Hello everyone, for this lesson we're going to discuss acids and bases and pH. So basically an acid is a proton donor, which is an H+. So normally hydrogen is one electron, one proton, and so this here is really a proton if it's an H+, because that electron's taken away. So an acid is a proton donor and a base is a proton acceptor. That's a strict definition of proton acceptor, but often I like to think of it as an OH minus donor. Okay, so a base is either something that accepts a proton or something that donates a hydroxide. Hydroxide being OH minus. So an example of an acid would be this hydrochloric acid, HCl. It splits up into H plus and Cl minus. Now. Another way to look at this reaction, and this is what you'll see in the textbook, I prefer just to consider the dissociation of the acid itself, but a lot of textbooks look at the acid interacting with water. So if I take this original equation and add water here, I'd have this, and that can split up into H3O plus and a Cl minus. So wherever you come across H3O plus in the book, just remember that it's really an H plus with a water, and so the H plus sort of resides on a water molecule, giving a total of 3 hydrogens, 1 oxygen, and an overall charge of H plus. So, I often use these interchangeably, but I usually just stick with this top sort of form. Then we have sodium hydroxide, and it can interact with an H plus to give sodium plus and the water. This is sort of showing the sodium hydroxide is a proton acceptor. So if there was protons around, the sodium hydroxide would take it up. Specifically, it's really the hydroxide portion that binds with the H plus to give the water. And the other way you could look at the base is just the fact that it's an OH donor, OH minus donor. And so bases are just compounds that are ionic, and they all have this, not all of them, but generally a lot of them have the OH component. So KOH is a base because we know that it splits up into K plus and OH minus. If we have a look at this compound here, which is supposed to be ethanol, but I realise that I haven't I've accidentally left 2 hydrogens off there. So if you have a look at ethanol, which is CH3CH2OH, it's not a base, okay, because we have the OH connected covalently to this carbon here. So really that's not a base, because the OH isn't free to dissociate away from this carbon. So wherever you have covalently bound OHs, so in other words, wherever the OH is bound to a non-metal, usually you're not going to have a base. In this case, the OH is bound to a metal, and so they're free to form ions, K plus and OH minus. And if you remember from our lectures with ionic compounds, generally, bar a couple of exceptions, ionic compounds are between a metal and a non-metal. And for this reason, this would not be a base, because it's not a non-metal bound with a metal, it's a non-metal bound with a non-metal. And generally when you have non-metals binding, you have covalent bonding rather than ionic bonding. And so here I've mentioned that it's not a base because it cannot dissociate. So that's a term we often use when we're talking about something splitting up into its ions. Now ammonia is a common base that we refer to. And the ammonia, if you look at the way that it reacts with water, it's going to form ammonium hydroxide. This here is a base that'll split up into NH4 plus and OH minus. So again, I can probably just show that that's going to go to NH4 plus, and you'd also have the OH minus associated with it. So it's a hydroxide donor. So Some other acids we have here. This is carbonic acid. So if you look on your can of soft drink, it'll say carbonated water. This is what it means. It's really carbon dioxide dissolved in water, and you'll form this, and that'll split up into 2H plus and 1 carbonate, or you might have a single H plus comes off, and you've still got HCO3 minus, which if you remember from our naming rules, this would be the carbonate, and this is the hydrogen carbonate because it's got the H associated with the carbonate, but colloquially we often call it bicarbonate. So if you look on a tin of baking soda, you'll see that it's sodium bicarbonate. It's really this is the bicarbonate part, and the sodium salt would be sodium bicarbonate. But nonetheless, that was just to show that we have this dissociation of protons away from the anion. Again, we have sulfuric acid in this case. So hydrogen sulfate is actually sulfuric acid when it's dissolved, and so it will split up into 2 protons and a sulfate, or you might just get 1 proton coming off and the bisulfate. HF is a weak acid, and you can see the HF splitting up into H plus and F minus. HBr is a strongish acid, and it'll split up into H plus and Br minus. So in all cases, the acid is donating this H plus, which is also known as a proton. So phosphoric acid, the same deal. It can lose up to 3 protons. Now, when you have an acid that can lose more than 1 proton, it's called polyprotic. Poly just means multiple, and so polyprotic means that you can lose multiple protons. So the hydrogen carbonate, the hydrogen sulfate, the hydrogen phosphate, so carbonic acid, sulfuric acid, phosphoric acid, these are all polyprotic because they can lose more than 1 H plus at a time. A monoprotic acid is an acid that can only lose 1 H at a time. So poly versus mono. Let's have a look at some conjugate acids and bases. So if you can just sort of ignore the red for the time being, we see we have water going with hydrogen iodide. This should really be an aqueous. So the hydroiodic acid splitting up into iodide and H3O plus. This is an acid because this is what's actually going to donate the H plus. It donates the H plus to this H2O, and so this is actually going to be the acid. The acid goes to the conjugate base because now we've just got the iodide, and if you look at going back the other way, the iodide can accept a proton, in this case from the H2O plus, and go back. That's why it's called a conjugate base. So conjugate sort of means exists in these pairs, like one complements the other. And so students commonly make a mistake here. They think you know, that the true acid is this, but the only reason this is acidic is because it got a proton from here. Okay, so this is the original acid. This is the original species that donates the proton. And so here, water is going to accept that proton. So overall, we have this proton is going to bind with the H2O to give us H0 plus. And so this is the base because it's going to be the proton acceptor. And so every base has a conjugate acid. And so the conjugate acid here is the H0 plus. And if you look at it, when we take this H0 plus and go back over the other side, it's going to lose the H plus to give us our water and our hydrogen iodide. So in that case, it's going to be a donor. And so it's the conjugate acid. So every base has a conjugate acid, every acid has a conjugate base. Okay, it just sort of depends on which way you look at it going over the arrow. So again, this is the conjugate base because when we go over that arrow, this species is going to accept an H+. Acetic acid with ammonia, for instance, this acetic acid is going to lose its proton and form this acetate species. This is the acid, this is the conjugate base. This is a proton donor. This is the proton acceptor when it goes back over through these arrows. So this, if I had enough room on the paper, it would be this here and that over the other side here. But I've drawn it on the line below because there's not enough room. So this is the conjugate base. This is going to be the conjugate acid because when it goes back across that arrow, so back across these arrows, it's going to lose its proton to form the ammonia molecule again, and the acetate would get that proton to form the acetic acid again. So hopefully that makes sense, and if you look at this video in conjunction with your textbook, it should make a bit of sense, I think. But it'll take a little bit of practice. With acids and bases, we often talk about strength of acids. We have strong acids and weak acids. HCl is a strong acid because we have a lot of that HCl splitting up into H+ and Cl-. This here is actually a very small arrow in the reverse direction. So this is showing an arrow in the forward direction. This is an arrow in the reverse direction. We often write it like this instead of having double-headed arrows. Often we use single-headed arrows. And the same thing with potassium hydroxide. It's going to be a strong base because it readily splits up into our K+ and our OH-. Weak acids and bases are like acetic acid. For example, the acetic acid doesn't really split up much to form our H+ and our acetate. It'll often stay in its associated form. It won't dissociate. It'll remain associated to a large degree. And ammonia is similar. When it interacts with water, it won't form a lot of this ammonium hydroxide, ammonium and the hydroxide. So it's all about the extent of dissociation. And so one thing that should be apparent, if you think about it, is that the conjugate base of a strong acid is weak. So if you have a strong acid like HCl, so I'll go back to that page. So if we have a strong acid like HCl, if it dissociates so much, it means that, and again, just make sure we're on the right path here, which is going to be the acid, which is going to be the conjugate base. This is the acid because it's going to donate the proton. This is not the acid. This is the proton itself. This isn't a proton donor, it's a proton. Okay? This has only come about because of the proton donor, the acid here. And this is the conjugate base. Because when we go back over the arrow, it's going to be the proton acceptor. Okay? So this is just the proton. Now, if this was a strong base, meaning if it readily picked up an H+, then you would form a lot of HCl. I mean, when the Cl- interacts with the H+, it forms the HCl. So it means that this really must be a weak base if we're going to have a strong acid. If the acid's really, really strong, meaning it splits up into H+ and Cl- really easily, the only way that's possible is if the reverse doesn't happen much. And the only way that's possible is if this conjugate base is actually weak. Okay? So, if we go back to our page here, it gives us an example with the HCl. And so just repeats what I've said. If we look at the acetic acid, the only way that this can be a weak acid is if this is a very, very strong base. if this is very, very strong base, then it will rapidly accept that proton to form this. So again, we know that this can only be a weak acid if the conjugate base is very, very strong. That's probably enough of that. Now, equilibrium constants, which we've covered before, we mainly refer to these with weak acids because strong acids dissociate so readily. We don't often think about Ka values and things. Ka being equilibrium constant for acid, A being acid. So when we look at this dissociation, we have again our products in the numerator and our reactants in the denominator. And so this isn't a liquid, this is aqueous. Okay, so its concentration does go into the denominator. And so that's the general expression for a weak acid. The larger the Ka, the stronger the acid. So the bigger this number is, means that the bigger these numbers are and the smaller this number is. And so that means if these are bigger numbers, it must mean that this forward reaction has occurred to a greater degree. So larger Ka means you have a stronger acid. Now we come to our water dissociation. In a normal, say, beaker of water at 25 degrees, we have water at any temperature, I guess, will dissociate to H plus and OH minus. But at 25 degrees in particular, the concentration of the H plus and the concentration of the OH minus are equal, and they're going to be 1 by 10 to the minus 7 mole per litre. You could just write this as 10 to the minus 7 because 1 times any number is just that number. And so we know that the H plus concentration and the OH minus concentration are both equal to 10 to the minus 7 moles per litre. This brings us to our water product, which if you multiply the H plus and you multiply the OH minus together, you'll have 10 to the minus 7 times 10 to the minus 7. And if you remember from basic math, you would just add the indices. You'll have 10 to the minus 14. And so that's the water product at 25 degrees. When you change the temperature, this number changes a bit. But for our purposes, we always just consider it at 25 degrees. This brings us to the pH scale, and I'm sure you've all heard of pH, but what does it really mean? The pH is defined as the negative logarithm of the H plus concentration. Make sure that you remember this is to base 10. So sometimes people get mixed up with log and think that it's the natural log, which is the base E. Generally nowadays people write the natural log as ln rather than log, but sometimes, particularly with older books, math books and so forth, log actually means the natural log. But anyway, just remember this is always to the base 10. And so if you rearrange this, you'll have H plus equals 10 to the minus pH. If you're familiar with math, then this should be pretty easy to see. If you're not, then it's not going to be as readily understood. But that's okay, as long as you can work with these two formulas, you'll be alright. So if we have a look at these different numbers, if for instance our H plus is 10 to the minus 7, as it is in neutral water, then you took the pH of that, the negative log of 10 to the minus 7 is 7. So neutral water has a pH of 7. Let's look at these other examples. 10 to the minus 6, you'd have a pH of 6. Now, it's important for you to understand that if you have 10 to the minus 7 and you have 10 to the minus 6, this is actually 10 times the strength of this. To go from 10 to the minus 7 to 10 to the minus 6, you have to multiply this number by 10. So comparing these two is like comparing one thing that's 10 times as strong as that. You'll notice that it's changed the pH by 1 unit less. So the lower the pH, the more H plus you have. I know it sounds counterintuitive, but the lower the pH, the more H plus. The more acidic is the solution. And if you have 10 to the minus 10, which is a very small number, so this would be 0.0, so actually 9 zeros and a 1, that would be 10 to the minus 10. This would be 0.6 zeros and a 1, 10 to the minus 7. So this is a much smaller number. This is 1,000th of this number. And the pH is much larger. it's a pH of 10. Try and do all these calculations on the calculator. So this calculator I've got here, if you pick one, say 10 to the minus 10, so on my calculator I would have 10 xy to the 10 minus there, like that, and that would give me 1 by 10 to the minus 10. If I take the log of that, then that gives me minus 10, and if I took the negative log of that, so because we have a negative log, then it gives me 10. Make sure you can use your calculator proficiently with those. Many of you might have one of these Texas Instrument calculators. I don't use mine very often, but if we had, it would probably go minus here, so minus, and then I'd have to push the log button, log, and then I'd have 10, and I push this hat to the power of minus 10, and I close it, and this should give us a pH of 10. So you can see the work I've done so far with the minus, the log button here, and then so it's that minus sign there, and then 10 to the minus 10. Sometimes, and so it gives us 10 for the pH of 10. Sometimes students will use this other way of doing it, that have negative log, and then they'd enter this as I forget how you do it on this calculator, but it'd be like 1 exponent then to the minus 10, and like I said, I forget on that. But if you're familiar with entering it that, just remember that this 10 to the minus 10 is really 1 by 10 to the minus 10. Just contact me if you have problems with that anyway. So that's our pH scale, and so let's look at an example question. So what is the pH of a 0.01 mole per litre solution of hydrochloric acid, and what is the hydroxide concentration? Again, make sure you remember that square brackets mean concentration. So HCl is a strong acid, so you have a negative log of the H plus concentration. Because it's a strong acid, we know that it's going to fully dissociate, and so we would have 0.01 as a concentration of the H plus, and so we get a pH of 2. Again, make sure you can do this on the calculator. So now for the hydroxide ion concentration, we have this water product, so H plus times OH minus equals 10 to the minus 14. You can rearrange that to give OH minus equals 10 to the minus 14 on H plus, and so 10 to the minus 14 on 0.01 equals 1 by 10 to the minus 12. So that would be the concentration of OH minus, or you could just write it as 10 to the minus 12. Again, make sure you can do these calculations, so pause the video as needed. So we have some acid-base reactions. Basically, if you add an acid, this is a general formula of an acid, to a base, you get water and a salt. Okay, so let's look at a specific example. If we have HCl plus NaOH, the hydroxide part, the OH and the H, come together to give water, H2O. So that would be H2O there, and then we have the Na and the Cl left over to give us sodium chloride, aqueous. You could write all this out as ions, so we'd have the HCl is really H plus and Cl minus split up, and the NaOH is going to exist as Na plus and OH minus separated, and so you put those together, the OH and the H plus is going to give us our water liquid, and we have our Na plus and our Cl minus, the sodium and the chloride ions, and so nothing changes with the Na plus and the Cl minus. They're both on the right and they're both on the left in the same form, and so we can call these spectator in the same way that someone that's watching football is a spectator. These ions aren't doing anything, they're watching, if you like, so we call the sodium plus and the chloride spectator ions. That brings us to our net ionic equation. The net ionic equation, you get rid of your spectator ions, so you just don't include them. And so if we remove from the previous equation, if we remove the chloride and the sodium, all we've got left are the H and the OH on the left side, and then on the right, if we remove them, you would just have the water. Sorry, my hands are the way. If you remove those, you just have the water. And so the net ionic equation is just the H plus and the OH minus giving you water, because these species are undergoing change. These are the ones that are actually undergoing some sort of reaction. The Na plus isn't doing anything, and the Cl minus isn't doing anything. They're just staying in solution. So that's covered a fair bit of material, and with these questions it's best just to practice and look at examples in the book until you understand, and please feel free to contact me if you still struggle with these things. Okay, thank you, and I'll leave it there.